So, gravity. We like gravity. Gravity is important. At this stage, as far as Newton was concerned, gravity is a force. In Newtonian physics, it absolutely is. So, what does it do? What does the force of gravity actually do to you? Lena. A force that pulls down to the center of the Earth. Absolutely. Here's a fun question then. What happens if we were actually able to get to the center of the Earth? There would be nowhere to go. The mass of the Earth around you would be pulling you gravitationally out. You would just kind of float there if it was hollow. Absolutely. That is what would happen. If you were able to get to the center of mass of the Earth, you would just kind of float there in space. I mean, obviously it's a solid iron ball. That's not going to happen. But if we were able to get there, it would be really quite a neat experience. So the force of gravity is a force that pulls down to the center of the Earth. But the Earth's not the only thing that has a gravitational impact. The moon has a gravitational impact on our planet. How do we see that? Tides. So you might not feel the presence, you might not be aware of the presence of the moon's gravity, but we see it all the time. That's how tides function. And so the gravity of the moon is pulling on the water on our planet towards its center. The reason that the moon is orbiting Earth is because Earth is pulling on the moon with its gravity towards its center, and the moon just keeps missing, which we'll talk about when we talk about universal gravitation in a little bit. So it's not just a force that pulls down to the center of the Earth, though that is absolutely where we're going to start. We're going to see in a little bit that the force of gravity actually acts between any two masses. So that you have mass means that you have a gravitational impact on anything around you that also has mass. So the classic old school pickup line is, well, there's a pickup line about attraction between two people because they both have mass. It's lame, but it exists. So what is mass? Mass is measured in kilograms. What is it? How would you describe what mass is? How big an object is? That's a good start. It's going to be a combination of those two. So how big an object is, Diego, before I come back to what you two said, what do you mean, Diego, by how big an object is?
The actual, how big it is.
Like the 3D space it takes up? Okay. So you're talking about the three-dimensional space it takes up? Well, let's use some examples here. So this box over here and this printer take up roughly the same amount of space.
Here.
So Diego, this box and this printer take up roughly the same amount of three-dimensional space. Which one's more massive? Why? So Lena, you said volume. And Liam, you said density. So volume is what Diego was kind of talking about here, is the 3D space you take up. Now, Liam's bringing us the idea of density. What's density? How would you explain that? How compacted it is. So how compact it is going to impact how many particles are going to be present in that three-dimensional space. They take up roughly the same space in space, but this one is more dense. This one's made of cardboard and mostly air. This one is made up of all sorts of metals and plastics. So it's not just the 3D space it takes up, it's also the particles that fill that space. So our definition for mass is going to be this. The total amount of matter in an object. Now, again, assuming I don't start chopping pieces off of you, is the total amount of matter in you going to change if I change your location? You're here in my classroom, I pick you up and I take you to Mr. DeVries' classroom. Or I pick you up and I put you on a boat. Or I pick you up and I put you on a rocket and send you to the moon. Does a change in location change the amount of matter in you? No. Unless I pull out an axe and start chopping pieces off of you, your mass is not going to change. And so as far as this goes, we say your mass is constant everywhere. And I mean, in physics, we are deliberate with the words we choose to use. Everywhere doesn't mean most places. It means literally all of the places I could conceivably put you in the universe, your mass isn't going to change. We're deliberate with the words we choose to use. So then, weight needs to be different. Because if you hop on a scale here versus you hop on a scale in space or on the moon, or you try and stand on a scale while I push you off a building, what's the scale going to read? If I push you off a building and you try to stand on a scale, what's the scale going to say? If there's nothing supporting the scale. Nothing. It shouldn't say anything. If we put you on, well, if you stand on a scale here in the classroom, the reading on the scale is going to be equivalent to what? Alexis, louder. Sorry? It is. The scale will always tell you your weight. But if you stand on it here in the classroom, that weight is going to be equivalent to, which is, what do we call that? Well, it's your mass. So if you were to stand on a scale right now, your mass and weight would be equivalent. We've said that your mass doesn't change, but that your weight can. I throw you off a building, you try and stand on that same scale, the scale is going to say 0. We haven't done it yet, but we're going to when we look at elevators in a couple days, or a week maybe. In an elevator, your experience of your weight changes. As the elevator rises, you feel heavier. As the elevator drops, you feel lighter. So your weight is changing, or your experience of your mass is changing. And if we take you up to space, your weight theoretically drops to 0. You are weightless. We say you're weightless in space. So then what is weight? If mass is the total amount of matter in an object, what's weight? How would you describe that? There's a few ways to think about it.
Like the mass when you're also taking account gravity.
Yes. Your weight is how gravity interacts with your mass. It's not just gravity though. Based on the kind of examples that I've given you here, if a scale cannot read your weight while you're falling through the air, what else do you need to be able to experience weight? Yeah. You have to have some surface holding you up against gravity. So it's not just how gravity impacts your mass, it is how gravity and normal force. Interacts with your mass. So mass is constant throughout the universe, but weight changes depending on where you are and what you're doing. So for those of you who are interested in going to space, the implication here is that anywhere where you are weightless is going to feel the same. And if while falling you are functionally weightless, going to space is going to feel like perpetually falling. So for those of you who don't like the feeling of falling, that moment while you're in the air before you impact the ground, being in space is going to feel like that all the time, which would be weird. And I would not enjoy that, but you might. So if weight is how gravity interacts with your mass, the formula that we use for the force of gravity is this. We say that big F with a subscript of g, that is the force due to gravity, is equal to your mass times little g. And this little g value changes depending on where you are. M stands for the mass of the object. The mass of the object experiencing the gravity. And then little g, we have a few different definitions for. Little g can be thought of as the acceleration due to gravity. Acceleration due to gravity. You measured this. I told you it was 9.8, and then you guys went out of your way to try and calculate it by dropping an object through a spark timer and then doing a bunch of graphs and analyzing things. Some of you got close, and that's great. Little g can be thought of as the acceleration due to gravity. It can also be thought of as something that we call gravitational field strength. And these ideas of fields are a little bit weird. You experience them all the time, but they are such a part of your guys' existence that you don't really acknowledge them. A gravitational field exists around any object with mass. The bigger the object, the more obvious the field is. And it's this gravitational field strength that causes the acceleration due to gravity. If we take you far enough away from the Earth, are you going to experience any gravity from the Earth? No. And so what we say then is you've left that gravitational field. You guys also experience electrical fields. How many of you guys got to play with the Van de Graaff generator in Science 9? So, Science 9? Yes, none of you? The Van de Graaff generator is the big ball on top of the thing, and you turn it on, and it like makes your hair stand up. Who was your Science 9 teacher? Lame. No, I totally did it. Yeah, then you were away. I do it every year. I shock my students. I take great pleasure in playing with the Van de Graaff generator with my 9s and my 12s. Science World has a different one. It's the plasma ball. That one's a little different. It still makes your hair stand up, but you're not going to shock other people. So you experience electric fields the same kind of way. You generate an electric field, whether you recognize that or not. But gravitational field strength, so an object that has mass has a gravitational field around it. The closer you are to it, the stronger the gravitational field is. And it has a value. We say it is 9.81 meters per second squared on or near Earth. Now, this does change as you get further away from Earth. When we say near Earth, we mean within, like, I don't know, 10 to 100 kilometers above the Earth's surface. That is near Earth. Anything beyond that, it starts to noticeably drop. Now, we said earlier that it was meters per second squared because it's an acceleration. But those aren't the only units we have for this thing. Because it is it's connected now to this force of gravity. Forces are measured in newtons. Masses are measured in kilograms. So if I isolate this thing for g, I have to divide by m. So I'm going to get Fg over m is equal to little g. So that's going to be newtons divided by kilograms. So we can say here as well that this number, 9.81, is also measured as 9.81 newtons per kilogram. So a meter per second squared can also be thought of as a newton per kilogram, the force applied to a mass. So this is the force of gravity. This little g varies depending on a few things. It changes depending on the mass of the object creating the gravity. The more massive you are, the more gravity you have. There's a whole bunch of yo mama so fat jokes related to this too in physics. Those are more of a 90s joke, really. So the mass of the object creating the gravity, the more mass of the object, the stronger the gravity, which is why things orbit around the sun in our solar system and not around anything else. The sun's the most massive object. It gets the orbits of everything else. And how close you are to that object. Again, the moon is a good example. You experience the gravitational pull of the moon all the time. You never notice it, though. Water does. The oceans do. The tides on our planet are as a result of this. But if you leave the Earth and get to the moon, now all of a sudden, the moon's gravity, at some point in between, and we're going to calculate that in a later lesson, at some point in between, the moon's gravity takes over. And then as you get closer to the moon, its gravity is what you experience. And the Earth's gravity is what you leave behind. So some examples. On Earth, at sea level, little g is 9.81 meters per second squared. On the moon, little g is 1.6 meters per second squared. On Jupiter, now we've never been to Jupiter, but on Jupiter, the acceleration due to gravity is 24.5 meters per second squared. So the gravitational strength of Jupiter is over twice what it is on Earth. So you would feel a lot heavier, even though your mass hasn't changed. On the sun, g is 275 meters per second squared. So I've got a YouTube video to demonstrate this. Where did it go? Nope, I'm not going to enter that. Dang it, where did it go? There we go. Okay. We'll do that, we'll do that. We'll do this. We'll do that. Okay. So this video has, it's not very long, but it's got a whole bunch of the car here. We're going to drop things on it. Same object. Sorry about it. We're going to drop the same object on it in different locations on our solar system. And we've got a bunch of different values here. Each one of these numbers on the object is the acceleration due to gravity in that location. So that's what it would look like to drop that on the car on Earth. On Mars, the impact is less, the bounce is greater. The same thing will look like on the moon. On Pluto, if you notice, the car bounced on its own. Almost no damage. There's Uranus. Saturn. Jupiter, largest planet in our solar system. Okay. What happened immediately? So the car collapsed. That wasn't an accident. For those of you who didn't notice, the first thing that happens, the car collapses. So that's the acceleration. There's no bounce. It's the acceleration due to gravity of an object on the sun. It's completely annihilated. So, let's take a look at, we'll just do some rough calculations. Let's determine what you would experience, what your weight would be on the Earth, the Moon, and Jupiter, and the Sun. So, I want you to write down whatever your mass actually is in kilograms. If you don't know, pull out your driver's license. If you don't know, I have a scale. Hop up. Here it is. What is your mass in kilograms? Is it in kilograms? Yeah. Hey, you should just be able to step on there. We'll go. No, it's dead. I'll be right back. kilograms of small numbers on the inside. It works. Accurate enough. Small ones on the inside. Mass in kilograms. What is it? Well, I don't need to know what it is. You just write it down in that blank. If you don't know your mass, fight. I'm not kidding. Go top on the scale. Figure it out. Whatever that number is goes there for you. And then we're going to figure out what your weight is in different spots. So, on Earth, with a mass, so I've got a mass of 100 kilograms. I want you to use yours. The force of gravity on me is going to be my mass, 100 kilograms, times the gravitational field strength, or acceleration due to gravity, 9.81 newtons per kilogram on Earth. So then my gravitational force, or the gravitational force on me, is going to be 981 newtons. That's me. Do your calculation, find the force of gravity on you. We're going to use these values here. We're going to find my weight on the moon. Now, weight is force of gravity. So Fg is going to be my mass hasn't changed, but now it's 1.6. So the force of gravity on me, on the moon, is 160 newtons. So let's just go for fun. Let's go back the other way and say, okay, if on the moon my weight is 160 newtons, what is the equivalent mass on Earth? So for this one, if I wanted to go back the other way and say, okay, this is equivalent Earth mass. Let's go back and roll that calculation. To find the equivalent Earth mass, we're just going to go back and say, okay, well, what does a 160 Newton force of gravity equal for a mass on Earth? For me, it's going to be 160 divided by 9.81. So if I went to the moon right now, I would feel like I have a mass of 16 kilograms. So to put that in context, this would be equivalent to a wolverine, like the animal, or a red-fronted gazelle, or a swamp wallaby, or a proboscis monkey, or a baboon. If you don't know what any of those animals are, then I can't help you beyond that. Okay, so my weight on the moon would be 160 newtons. That is the equivalent of having a mass of 16 kilograms on this planet. So let's go look at Jupiter. Your weight on Jupiter. Fg is equal to, mine is going to be, my mass is 100. The acceleration due to gravity on Jupiter is 24.5. So for me, that's 2,450 newtons is the force of gravity on me on Earth. Find your value. And then let's go work it backwards. That means on Earth, I would have the equivalent mass of 2,450 equals m times 9.81. My equivalent mass on Earth would be roughly 250 kilograms. So now let's go up on the animal chart again. This is basically something called a gray seal. Or for those of you who are more comfortable working in pounds, that's 500 pounds, 550 pounds. And now let's go figure out the force of gravity on the sun. Mine's going to be 100 times the acceleration due to gravity, 275 on the sun. So my calculations are easy. 27,500 newtons would be my weight on the sun. My equivalent mass on Earth would be this 27,500 equals m times 9.81. My Earth equivalent mass would be 2,803 kilograms. So on the scale of animals, that's equivalent to something called a beaked whale. It's slightly smaller than an Asian elephant, is what I would feel like on the surface of the sun. Never mind, it would be very hot. But as far as my mass goes, my equivalent mass, my experience of my mass, would be equivalent to becoming an elephant on Earth, which would be wild. Does anyone want to share their values? Here day. So 600 and, okay. So then what is your equivalent mass from the moon? Yeah, the equivalent mass. 10.4. So that would be like taking you, and now all of a sudden you turn into a Canadian lynx. A lynx. Or a honey badger. Or an average sized dog is what you would experience your mass as on the moon. Let's go to Jupiter. What was your equivalent mass on Jupiter? Okay. Does anyone else have an equivalent mass on Jupiter? 176 kilograms. So, Vian, you are turning into a lion. A very large. You would experience your mass as though you were lion-sized on Jupiter. How about on the sun? What's your equivalent mass on the sun? 1,190? 1,900. Okay, so you're basically a rhinoceros. A white rhino is what you would experience. So, not insignificant. Cool. So, an interesting activity is the one that we're going to do next. You do have time to do this. You're going to do this in partners. What you're going to do here, we're not handing this thing in. Actually, maybe I should get you to hand it in. Yes, we're going to hand this thing in. I'll decide afterwards if we hand this thing in. Here's an activity for you. I want you to figure out how high you would jump if we teleported you to the moon. So you're going to do this in partners. What you're going to do is you're going to measure your best vertical on Earth. It's going to be an awkward jump. It's going to be a straight-legged vertical. You got to keep it straight. Like, so you're going to, so it's effectively, it feels as awkward as it sounds. You're going to crouch, you're going to jump, your straight leg vertical. You can measure how high that is on Earth. So it's easiest to do this in groups of 3, actually. 1 to do the jumping, 1 to do the measuring, and someone to take a picture of what's going on, or film it with their camera. This is what you're going to try and do. You're going to find the initial velocity of your jump. We're going to assume that your initial jump velocity is going to be the same on all these places, which isn't true, but we're going to assume that it is. To find your initial velocity, we know what the acceleration due to gravity is. We know what the final velocity at the top of your jump is. It's 0. And we know what the acceleration due to gravity is on Earth. We know VF, we know D, we know A. We can find VI, the speed at which you leave that node. Assuming that holds true, you're going to find your velocity, your vertical, the height you travel, your displacement, and how long you'll be in the air on the moon and on the sun. Now, the one assumption that isn't true is that your initial jump velocity is going to be the same, because obviously it's going to be easier to push your mass up on the moon, it'll be harder to push your mass up on the sun, but assuming it's not, give us a ballpark for how high you're going to jump on the Earth and on the sun. Okay, give it a shot. See what you can do. Get up. Find a partner. Group of 3 or group of 4 is better for something like this. What do you get? Yes, you're all jumping. Holding the meter stick up against the wall, or taping the meter stick up against the wall and then filming it is a really great way to see. I got a bunch of meter sticks. Sorry? Yes, whatever tools you need. I got space all around the room. There's empty wall at the back and on the side. If you want some tape, here it is. Figure out what your vertical is on Earth. So then your initial jump velocity. Yeah, keep it in this little area here. There's no reason to go further than that, but yeah, you can leave the class. Straight leg vertical means it's going to be really hard to do. To clear the meter stick. Okay. Okay.
Are we timing it too?
You don't need the time, you just need the vertical. Yeah, as high as you can. So you want to make sure that you want it as level as possible. With whatever her height is. Because any sort of angle is going to change how you read. So a couple practice jumps just to get an idea. Come on, Diego, you can do better than that. Come on. Okay, so convert that to meters. Yes, it should all be meters. Don't lower, Diego. Lower. You can do it. Where's my scale go?
Basically, have the black line. So look at the black line and go straight up.
Okay.
You get it, go fix it. Yeah, like I think 12.5.
You guys got your verticals? Nice.
It's so awkward to do a straight line.
Yes, it really is. It really is.
When you first said it, I thought you meant like this, like one of the kind of vertical ones.
Oh no. Because I had students, part of the reason we wanted the straight leg vertical. Wait, fine. How did you get 180 centimeters?
18 centimeters.
18 centimeters. Part of the problem we were having with not the straight leg vertical is I had students easily clearing the meter stick.
Oh well, yeah, because you just lift your legs up. Like I could.
Yeah.
Yeah.
Like Nick Martino was one a couple years ago. He was a rugby player. I think he also played football. Like he had just an insane vertical.
Yeah, no,
And when he pulled his legs up, he was way beyond the meter stick. And volleyball players would be the same, so we had to do the straight leg.
Well, you could technically, like, in the weight room, they just measure where you put your hand right against it,
Yeah.
and then you jump and place the thing in tape. Like, there's people hitting over 10 feet. Max.
Well, yeah, and then subtract.
And then,
Yeah,
subtract,
right.
Yeah.
So I guess we could do it. We could do it that way too. It would be no different. Harder to measure, but same idea. Well, yeah. If you want to take a running start, go for it. Yeah, why not? It shouldn't change it that much. Let's see how much it changes it.
Are you supposed to bring your legs up in the air?
No, you want to keep because I want everyone roughly the same experience with this. And I had people, like I was saying to these guys, I had people in the past who were easily clearing the meter stick when they would pull their legs up. It's fairly old.
What did you say?
Okay, so what's that in centimeters?
That's over a foot. Wait, jump right now. There's no way you're hitting it. 21 centimeters. Actually, okay, that's way more realistic. That's a meter. If you're that's entirely vertical.
Okay. Okay. Cool. Okay. Okay. Bell's going to go here in a couple of minutes. Actually, a couple seconds. At some point in the next minute and a half, Bell's going to go. This does not need to be completed for homework. We have a shorter-ish block tomorrow. So you'll have time to finish this tomorrow. And you guys are going to be working on this tomorrow as well. The FET lab. If you want your computer, bring it. If you otherwise, you're going to be using some of the school's Chromebooks. When the bell goes, you may also go. Like I said, you'll have time to finish this tomorrow. Have a great day. We'll see you later.